Hi everyone, welcome back. It's Thursday and we need to look at 2 new rules before you take your quiz tomorrow, okay? But so far we have talked about 3 rules. The first, we're dealing with 2 chords that intersect inside of a circle. So when you have something like this, you want to take one of the chords, let's say this chord here, we multiply piece times piece. So A times B for one chord and set that equal to, for the second chord, piece times piece, C times D, okay? When you have 2 secants that meet on the outside, they have a common external point, then you want to think about outside and whole. Okay, so for the first secant, we take the measure of the outside which is A, and multiply that times the measure of the whole secant segment. To get that whole measure, you add A plus B, outside plus inside. And then you do the same thing for the second secant segment. Take the measure of the outside part, which is C, and then multiply that times the measure of the whole thing. To get the measure of this whole thing, we add the outside plus the inside, C plus D. And then for the third scenario, you could have a secant and a tangent that meets at a common point on the outside. Okay? So, once again with the secant, you take the measure for the outside, which is A, and multiply that times the measure of the whole secant segment. To get the whole measure, we add the outside plus inside, A plus B. But for the tangent, we take that one measure and we square it. So we have our equation. Let's solve. Okay? Now, for the new rule, we're looking at segment lengths using properties of tangents. We have 2 tangents involved for this particular problem. What is a tangent? It's a segment that touches the circle at one point. We have a point of tangency. All right. But in order to use this theorem, we need to prove it first. So we're about to do that now. So given the figure below, prove that segment SP from point S to point P is congruent to segment TP, from point T to point P, okay? All right, so first of all, we're given that the measure of angle PSO, as we can see here, it is a right angle, so it's 90 degrees. Likewise, angle PTO, it is a right angle, so it is also 90 degrees. Let's just say that was given to us, okay? For our second statement, we can show that the measure of segment SO from point S to point O is the same measure as segment TO. So let's place some tick marks here. How do we justify that these 2 segments SO and TO are congruent? We discussed this before. These are both radii of the same circle, so they are congruent. All radii are the same circle are congruent. All radii of the same circle are congruent. Then, can you make sure they see this? Okay? Likewise, we can also show at step 3 that segment PO is congruent to itself. Why do we want to show that segment PO is congruent to itself? Because segment PO is a common side for both triangles. Okay? So it's congruent to itself. Let's go ahead and put double tick marks here. And this is by the reflexive property of congruency. And so, if this segment is congruent to itself, then we can show that its measures are equal. And this is by the definition of congruent segments. Definition of congruent segments. So now we're at the point where we can show, and this is what we were striving for, to show that triangle, add a triangle here, that triangle PSO is congruent to triangle PTO. So now we can show that these 2 triangles are congruent to each other. Okay? By which reason? We have 5 reasons we can use. But in this case, we notice that we are dealing with right triangles. And we have proven that their hypotenuses are congruent to each other. Segment PO is the hypotenuse for each one of these triangles, right triangles. And likewise, they have a pair of corresponding legs that are congruent. So this is by the hypotenuse leg congruency theorem. Hypotenuse leg. And so, if that is the case, we can now prove that segment SP is congruent to segment TP. They are congruent to each other. And let's add to this. We can now prove that segment SP is congruent to segment TP. By which reason? They are corresponding parts of congruent triangles. That is CPCTC. So now that we have proven this theorem, we can apply it anytime we need to. But what did we just prove? We just proved that anytime you have 2 tangent segments from a common external point. Once again, if you have a circle, and if that circle has two tangent segments from a common external point, they meet at a common point, then from that common point to the point of tangency, once again, from that common point to the point of tangency, they are congruent or equal in measure. So these two segments are congruent. You will see those a lot on standardized tests. Do not forget this rule. So let's look at a few problems that apply this rule. Okay? Where do we see where we have two tangents? If you look at the first problem on the worksheet, you don't have two tangents. This is a tangent, but this particular segment here, it can go through. It can be a secant. So we only have one tangent, so we can apply that rule there. But if I look at problem 2, oh, I see a tangent and a tangent. This is the point of tangency, this is the point of tangency, and they both meet at a common external point. So we can apply that rule here. Okay? So if that is the case, then we can show that this segment has the same measure as this segment. So these two segments are equal. So to set up our equation, we just set x squared equal to 16, and then solve. To solve this, we take the square root of both sides, and we find that x is equal to both the positive and negative of 4. We're through. Do we have two tangents here? No, we have one tangent. What about here? Do we have two tangents? No, we only have one point of tangency. What about with problem 5? Yes. Point S is a point of tangency to this circle, point T is, and they both share a common external point. Therefore, the rule can apply here. So from point S to point R is the same measure as going from point T to point R. So we can set these two measures equal. So you set 2 times x plus 4 equal to 26. And now isolate x by moving 4 first. That leaves 2 times x is equal to 22. Divide each side by 2. In this case, we find that x is 11. X is 11. Okay? And if you look on the back side, when do we apply this rule again? If you look at the first section, you don't have two tangents. So therefore, we cannot apply this rule with problems 1, 2, and 3. However, when you look at problems 4, 5, and 6, oh, it kind of look like a clown hat, like I always tell y'all, clown hat, when you have two tangents. All right, if that's the case, then these two segments are equal. So we can set 4 times x plus 7 equal to 7 times x minus 8, and then solve. Same here. Those two segments are equal because they have two tangents. All right, so we can set 3 times x squared minus 10 equal to 17. Let's complete this because some of you will look at this problem and think, oh, that is hard. It's really simple. All you need to do is move the 10 by adding 10 to both sides of the equation. That leaves 3 times x squared is equal to 27. You want to get rid of the 9 before you undo your square, so you want to divide each side by 3. That leaves x squared is equal to 9. And then we take the square root of both sides and find that x is equal to both the positive and negative of 3. And we're through. And then you do the same with 6. So that is how you set up an equation when you have two tangents involved. Okay? But we want to learn one other rule, so just hold on for a minute.